Today we're going to be talking about the dye dilution method for measuring cardiac output. Essentially, the dye dilution method tells us that a particular amount of dye is injected into the heart. In our case, 6 milligrams of dye is injected. And we measure after the time of injection, at particular intervals, whether it's every second, every 2 seconds, we measure the amount of dye that still remains in the heart. And the amount of dye remaining is modeled by this function here, C of t. And this method allows us to find the cardiac output, which means the amount of blood that the heart pumps out every second or 2 seconds or whatever. So the formula that we use for cardiac output is F for flow or flux is equal to A, which is the amount of dye, in our case 6 milligrams, divided by the integral from 0 to t, so this is our time of measurement here, of our function C of t. So because we've been given the function, and because we've been given our time interval, in other words, we're going to measure the amount of dye remaining from the time that we inject at 0 until 10 seconds after injection, we can plug 0 and 10 into our equation here. So we're going to get an equation for flow or flux. And again, we have 6 milligrams of dye, so we're going to have 6 divided by now this integral here. So the integral will be always from 0, the time of injection, to time t, which is the time at which we stop measuring. And in our case, that's 10 here. So we'll put 10 in, and then we'll plug in our equation for the function C of t. So we'll get 20 t e to the negative 0.6 t dt. And obviously the only difficult part now of this is finding the integral. And in this case, we'll need to use integration by parts in order to take the integral. The first thing we can do, though, is we can pull the 20, which is a constant coefficient on this product here. We can pull the 20 out in front of the integral, and it'll get removed here. We'll put 20 in front. And so now we'll have 6 over 20, which of course can reduce to 3 over 10. So what we'll actually have here is 3 over 10 times the integral from 0 to 10 of t e to the negative 0.6 t dt. And we can use integration by parts to take this integral. So for integration by parts, we'll set u equal to t. We will set dv, the other part of the integration by parts formula, equal to e to the negative 0.6 t dt. We'll take the derivative of u to get du, and of course the derivative of t is just 1, so we have 1 times dt, or just dt, and we'll take the integral of dv to get v. The integral of this will be 1 over negative 0.6 e to the negative 0.6 t. Now we'll plug these into our integration by parts formula. Remember, the integration by parts formula tells us that if we have the integral of u times dv, that's going to be equal to u times v minus the integral of v times du. So we'll multiply u times v, and we'll get F is equal to, we'll get 3 over 10 times here u times v. So u times v will give us 1 over negative 0.6 times t e to the negative 0.6 t minus, because we have minus here in our formula, minus the integral of v times du. So v and du here, we essentially just have v and dt. So we get 1 over negative 0.6 e to the negative 0.6 t dt, and that's our formula there. Now we can actually evaluate this integral quite simply, but first let's go ahead and simplify a little bit. We'll get 3 over 10, and then 1 divided by negative 0.6 is the same as 1 divided by negative 6/10, which is the same as 1 times negative 10 over 6. So essentially we have negative 10/6 here, so we'll get negative 10 over 6 t e to the negative 0.6 t, and then we can pull this constant coefficient out in front of the integral, our negative signs will cancel, so we'll get plus, and then again here, 1 over 6/10 is the same as 10/6 times the integral of e to the negative 0.6 t dt. Now we can go ahead and evaluate the integral. So we'll get 3 over, and the integral here will be 1 divided by negative 0.6 in the front here. So that's of course 1 divided by negative 6/10, which is the same as negative 10/6. So we'll get negative 10/6 e to the negative 0.6 t. And the important thing to remember here is that we're going to be evaluating this whole thing on the range 0 to 10. So the 0 and 10 that we had right here, we have to carry all the way through and evaluate on this range. So we'll go ahead and do a little bit of simplifying here. And now we can go ahead and evaluate from 0 to 10. So we'll plug 10 in first here, and then we'll subtract whatever we get when we plug in 0. So we'll get f equals 3 divided by 10. And now here we'll plug in 10, so we'll get negative 10/6 times 10 e to the negative 0.6 times 10 minus 100 over 36 e to the negative 0.6 times 10, and then we'll subtract whatever we get when we plug in 0. So we'll subtract here. Our first term will go away because we'll get 0 here for t, and that'll obviously negate everything here. Then we'll get negative 100 over 36 e to the 0 is just 1, so that'll become 1. And now we can just finish our simplification. We'll simplify the coefficients and the exponents. We'll distribute the 10 and then start factoring. We'll find a common denominator and then simplify 3 over 1,000 over 6. Factor out 1/6 and then simplify the coefficients again. Then just reduce the fraction. Now if you do this on your calculator, you're going to get one number that gives you the cardiac output in seconds. If you want to find the cardiac output in minutes, you just multiply your answer by 60, and what you get is F equals, or a flow or a flux of 6.6 liters per minute. This is the amount of blood that the heart pumps out in liters every minute. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.